Hello everyone, this is the presentation for the course Topics in Data Science. My name is Gao Gao. I'm a PhD student of Computer Science Department at UMass Law. I will talk about deep contextualized word representations. This paper was published in 2018. Because of my research file is about human-computer interaction, so I didn't have much knowledge about the language model in NLP. I'm not sure I could be 100% to understand the paper very deeply. So I find some learning materials of this paper and several explanation lectures of this paper. I just try my best to understand it and give my explanation of what I learned from this paper. Before I talk about the paper detail, I would like to talk some background knowledge about language modeling embeddings, which I try to learn at the beginning. So I have several questions in my learning process. The first one is what is NLP? I try to find some definitions from Google, and it says the natural language processing is a subfile of linguistic, computer science, information engineering, and artificial intelligence concerned with the interaction between computers and human languages. In particular, how to program computers to process and analyze large amounts of natural language data. The second one is what is a language embeddings and what is embedding from language model. As we all know, the language is very complex and the context can be completely change the meaning of the individual words in a sentence. Here I have two sentences. That's right, and please turn right. In these two sentences, the words right are the same, but they have different meanings. We can easily decipher this complexity in the language. But if we want to create a model to understand different meaning of the nouns in the given surrounding text, it's very hard. The third one is what is word embeddings? So now we have some word embeddings like the word to vector, fast text. They can just represent per words, so they cannot capture how the meaning of each word can be changed based on the context. So now let me go back to talk about this paper. In this paper, I would like to talk about 5 parts: introduction, model approach, evaluation of the model, analysis, and conclusion. For the introduction part, the natural language was very difficult to work directly. It would better transform the representation for something like machine readable. Learning high quality representation can be challenging. The pre-trained word representation should model with several characters. Here, I list 2 of that. The first one is the complex characteristic of the word use. The second one is how these uses vary across linguistic contexts. So in this paper, it introduces a new type of deep contextual word representation, which is different from the traditional word embeddings. The paper used vector derived from bidirection LSTM that is trained with a coupled language model objective on the large context corpus. So it's called embeddings from language models. This model, in the sense that they are the function of all the internal layer of the bidirectional language model. Combining the internal states in this manner allowed for very rich word representations. The previous approaches for learning words vector only allow a single context-independent representation for each word. So now we will also talk about the contribution about this paper. This paper leveraging language modeling called embedding from language models to get pre-trained contextualized representation using intrinsic evaluations. So the paper shows that higher level LSTM states capture context dependence aspect of word meaning. Extensively, the experiment demonstrates the embedding from language model can representations word extremely well in practice. It's easily to add existing model for 6 challenging NLP problems. I will talk the 6 challenging NLP problems later. The model approach. The embedding from language model word representation are the functions of the entire input sentence. They are computed on top of 2 layers bidirectional language models with the character convolutions as a linear function that of the internal network state. This allows to do semi-supervised learning, where the bidirectional language model is pre-trained as a large scale and easily incorporate into a wide range of existing natural NLP architecture. So the first one is bidirectional language models. In the embedding from language model, it uses a two-way LSTM language model consisting of a forward and a backward language model. The objective function is to take the maximum likelihood of the language model in the 2 actions. And after pre-train this language model, the embedding from language model is used as the word representation according to the following formula, which is to sum up each intermediate layer of the bidirectional language model. The simplistic of one can use the highest level representation as embedding from language model. The embedding from language model. When performing a supervised NLP tasks, embedding from language model can be directly spliced into the work vector input of the specific task model or the highest level representation of the model. So, unlike the traditional word vector, each word corresponds to only one word vector. Embedding from language model uses a pre-trained two-way language model and then derived context-dependent current word representation from the language model based on the specific input. So the representation of the same word is not the same, and then added to the specific NLP supervised model. Using bidirectional language model for supervised NLP tasks. A pre-trained bidirectional language model and the supervised architecture for the target NLP task is a simple process to use the bidirectional language model to improve a task model. Run the bidirectional language model and record all the layer representations for each word. Then let the end task model learn a linear combination of these representations. It's beneficial to add a moderate amount of dropout to embedding from language model, and in some cases, regularize the embedding from language model weights to be lost. This imposes an inductive bias on the embedding from language model weights to stay close to an average of all bidirectional layers. So the pre-trained bidirection language model architecture, it have three characters of this model architecture. The first one, the pre-trained bidirectional language model in this paper support joint training of both direction and at the residual connection between LST and layer, which highlighted the importance of using bidirectional language model over forward-only LMs and the large-scale training. The second one, the bidirectional language model, provides three layers of representations for each input token, including those outside the training set due to the purely character input. The third one is once pre-trained, the bidirectional language model can compute representations for any task. In some cases, fine-tuning the bidirectional language model on domain specific data leads to significant drops in perplexity, and one just increase the downstream task performance. So the evaluation of the model. In the evaluation part, the work evaluated the embedding from a language model in some common NLP tasks, which include the question answering, textual entailment, semantic rule labeling, reference resolution, named entity extraction, and sentiment analysis. So the first, they built different model for each task as a baseline, and then join embeddings from language model. You can see that all 6 tasks have been proved after joining embedding from language model, and the average can be increased by more than like 2 or 3 percentage points. At the final result, exceeded the previous advanced result. For the analysis part, in the analysis part, we can see that the effect of using all layers is better than using only the last layer of embedding from language model. On the input or output plus embedding from language model, effect is not conclusive. Different tasks may have different effect. So here, the first one is the alternate layer weight schemes. We could see the large values such as the lambda seems to 1 effectively reduce the weight function to simple average over the layers, while smaller value like the lambda is seem to be 0.001 allow the layer weights to vary. So we could see use the embedding from language model have very good performance than the one they didn't use. Where to include the embedding from language model? The including embedding from language model at both the input and output layer for SNLI and SQUAD inputs over just the one input layer. But for SRL, performance is the highest when it's included at just the input layer. What information is captured by the bidirection uh, language models representations? It have three things. The first one is word sense disambiguation. The second one is POS tagging. The third one is implication for supervised tasks. Now we will talk about sample efficiency. Adding embedding from language model to a model increases the sample efficiency considerably, both in terms of the number of parameters updated to reach state of the art performance and the overall training success. After we adding the embedding from language model, the model exceeds the baseline maximum to approach 10, like the nearly 98% relative decrease in the number of updates needs to be reached the same level of performance. So the figure shows that it's a comparison of baseline which is the embedding from language model performance for the SNLI and the SRL, as the training set size is varied from 0.1% to 100%. Additionally, the embedding from language model enhances model use smaller training set more efficiently than the model without using embedding from language model. So the improvement with the embedding from language model are largest for smaller training set and significantly reduce the amount of training data need to reach like a given level of performance. And in SRL case, the embedding from language model with 1% of the training set has about the same F1 as the baseline model with 10% of the training set. Then we will talk about the visualization of learned weights. So this figure shows that the visualization of softmax normalized bi-direction language model layer weights across the task and the embedding from language model locations. So the normalized weights less than 1/3 are hatched with the horizontal lines, and those greater than 2/3 are speckled. So as the input layer, the task model favors the first bidirection language, like the language model layers. For co-reference and the SQUAD, this is strongly favored, but the distribution is less peaked for the other tasks. The output layer weights are relatively balanced with the slight performance for the lower layer. We'll talk about the conclusion. So, a general approach for learning high quality deep context dependent representation from bidirectional language models. This approach shows large improvement when applying embedding from language model to a broad range of NLP tasks. Through the experiment, it's confirmed the bidirectional language model layer is efficiently encode different types of syntactic and semantic information about a word in context. And its use all layers improves overall task performance. Thank you for listening my presentation.